A quick reminder of where we are. We're involved with determining heat of a chemical reaction, and we've learned that there are actually two means of expressing heat of reaction: delta U, change in internal energy, and this is appropriate during a constant volume process. Most often, we're going to be involved in calculating delta H. It's a change in enthalpy during a constant pressure process. It's much easier to leave our experiment open to the atmosphere and therefore ensuring a constant pressure rather than a constant volume process. So we're usually concerned with change in enthalpy, delta H. Thus far, we've learned three ways to determine the heat of reaction. Calorimetry, Hess's law, using the enthalpy of formation of reactants and products, and it's the sum of the products minus the sum of the reactants gives us the value for delta H of reaction. Now we're going to talk about estimating the heat of reaction from bond dissociation energies, and it's essentially bonds broken minus bonds formed. We want to remind ourselves of a few facts. The bond breaking is endothermic. It requires energy, and therefore the reverse process, bond making, is exothermic. It releases energy. When we estimate the heat of reaction from bond dissociation energies, we sum up the energies involved in breaking all of the bonds, and from that value, we subtract the energy that is gained by forming all of the bonds. This is a very good representation of the process. We're looking at the combustion of methane and oxygen. Our products are going to be CO2 and water. Energy of our reactants is represented by this height of this line. So remember, our energy is going to be increasing as we move up. In order to reach what we call the separated atoms limit, energy has to be put into the system to break all of these bonds. Bond breaking is endothermic. It requires energy, so the separated atoms limit is at a higher energy than the reactants. We put in energy, roughly about 4 times the average energy of a carbon-hydrogen bond, plus 2 times the average energy of an oxygen-oxygen double bond. So we have a higher energy separated atoms limit, and energy is going to be released as all the bonds here are being formed. Bond making is exothermic. So the energy that is released as we go back down is approximately 2 times the energy of the carbon to oxygen double bond and 4 times the energy of the hydrogen to oxygen single bond. Overall, we see the products are at a lower energy level than the reactants, which matches the fact that the delta H is exothermic, is negative. These values here, the bond energies, these are average bond energies. The energy of an oxygen-oxygen double bond is measured for thousands of compounds, and then the average taken of that value. Same thing occurs with the carbon-hydrogen and oxygen-hydrogen. All of these bonds, they're average bond energies that were obtained from thousands of compounds. This is a table of average bond energies that can be used to estimate the heat of reaction. Let's go through the process of estimating the delta H for the reaction of the combustion of methane. We would start by drawing our Lewis dot structure for each of these atoms. All right, and we take a look and see at the bonds that we need to break. We need to break the 4 carbon-hydrogen bonds, 2 oxygen-oxygen double bonds, and we're going to make 2 carbon-oxygen double bonds, and we're going to use the value of 799 kilojoules per mole for CO2. We're also going to make 4 oxygen to hydrogen single bonds. So we have delta H of reaction is approximately equal to the bonds broken minus the bonds formed. Okay, and note here, if the sum of the bonds formed is a larger value than the bonds broken, it's going to be an exothermic reaction, as this would be a larger value subtracted from a smaller value. So this is approximately 4 times a carbon-hydrogen bond plus 2 oxygen double bonds in CO2 minus 2 carbon to oxygen double bonds plus 4 hydrogen to oxygen single bonds. Okay, we look up our values. And we get our value of minus 818 kilojoules per mole. And this value is within about 10% of the actual value. Let's work another problem. We'll estimate the delta H reaction for the chlorination of methane. We're going to use bond dissociation energies. So the first step is we'll draw the Lewis dot structure of all the reactants and compounds. Break them all, make them all. So we're going to break all of these bonds and then make all of these bonds. So delta H is approximately going to be equal to 4 carbon to hydrogen bonds plus 3 chlorine to chlorine. And we're going to subtract all the bonds that are formed. We have 1 carbon to hydrogen and 3 carbon to chlorines and 3 hydrogen to chlorine bonds. Okay, we'll look up the respective values in our table. And our result is minus 330 kilojoules per mole of reaction.